Proceed. Exercise 4.1. Principle of mathematical induction. Now we will see question number 5. This is 1 into 3. 1 into 3 plus 2 into 3 square. 1 into 3 plus 2 into 3 square plus 3 into 3 cube plus dash dash, and the last term n into 3 raised to the power n into 3 raised to the power n equals to 2n minus 1 2n minus 1 into 3 raised to the power n plus 1 plus 3 upon 4 plus 3 and whole upon 4. So we have to prove this by the method of induction. So the first step, we will prove LHS and equals to RHS by putting n equals to 1. So for first step, we will write for n equals to 1. Put the value of n equals to 1 in the last term of the LHS. So LHS is n into 3 raised to the power n. And when we put the value of n equals to 1, then it becomes 1 into 3 raised to the power 1, and that is 3. So we get the LHS as 3. Now in RHS, put the value of n equals to 1. So the RHS is 2n minus 1 into 3 raised to the power n plus 1 plus 3 upon 4. And put n equals to 1. So 2 into 1 minus 1 into 3 raised to the power 1 plus 1, 2 plus 3 upon 4. 2 minus 1, 1, and 3 square 9, 9 plus 3 12, 12 divided by 4 we get 3. So for n equals to 1, LHS is equals to RHS. So we will write it is true for n equals to 1. Because for n equals to 1, LHS is equals to RHS. So we will write that it is true for n equals to 1. And for the next step, we suppose let it is true for n equals to k. It is true for n equals to k. This we have supposed. And at the place of n on both sides, we will put k. So 1 into 3 plus 2 into 3 square plus 3 into 3 raised to the power 3 dash dash, and at the place of n we will write k into 3 raised to the power k equals to 2k minus 1 and 3 raised to the power k plus 1 plus 3 whole upon 4, and name it first number equation. Now the third step, to prove it is true for n equals to k plus 1. To prove it is true for n equals to k plus 1, so first we write the term up to k. So 1 into 3 plus 2 into 3 square, 3 into 3 cube plus dash dash k into 3 raised to the power k. Then we will write the next term k plus 1th term. So at the place of k, we put k plus 1 and again into 3 raised to the power. At the place of k, we will write k plus 1. And on the right side, we replace k by k plus 1. We replace k by k plus 1. So 2 into k plus 1 minus 1. 3 raised to the power k plus 1 plus 1 means k plus 2 and plus 3 upon 4. So this becomes 1 into 3 plus 2 into 3 squared plus 3 into 3 cube plus k into 3 raised to the power k plus k plus 1 into 3 raised to the power k plus 1. After solving this 2k plus 2 minus 1, it becomes 2k plus 1 into 3 raised to the power k plus 2 plus 3 upon 4. Now we will prove LHS equals to RHS. So for LHS, up to k into 3 raised to the power k from first number equation up to this term, we can write the term RHS. So up to this, we will write 2k minus 1 into 3 raised to the power k plus 1 plus 3 upon 4. And this last term would be written plus k plus 1 into 3 raised to the power k plus 1. Now we take the LCM. So from these two terms, the LCM would be taken 4. So 4 is taken LCM. Then we get 2k minus 1 into 3 raised to the power k plus 1 plus 3 and plus 4 into k plus 1 into 3 raised to the power k plus 1. From numerator, from these two terms, there is common 3 raised to the power k plus 1. From these two terms, there is common 3 raised to the power k plus 1. So 3 raised to the power k plus 1 is taken common from first and last term. So it remains 2k minus 1 plus 4k, 4 into k, 4k plus 4 and plus 3 as it is, whole upon 4. So 2k plus 4k, 4k plus 2k, it becomes 6k and 4 minus 1 plus 3 and 3 raised to the power k plus 1 plus 3 upon 4. Inside the bracket, 3 is taken common. So we get 2k plus 1 and 3 raised to the power k plus 1 plus 3 upon 4. So 3 raised to the power 1 and 3 raised to the power k plus 1. In multiplication, powers be added. So 2k plus 1 and 3 raised to the power 1 and 3 raised to the power k plus 1, it becomes 3 raised to the power k plus 2 plus 3 upon 4. So we get RHS. After solving LHS, we get RHS. So it is true for n equals to k plus 1. Thus, it is true for n equals to k plus 1. Hence, it must be true for n equals to k and n belongs to capital N. N belongs to natural numbers. Now question number 6. One into two plus two into three. One into two plus two into three plus three into four. Plus dash dash n into n plus 1 equals to the term containing RHS n into n plus 1 n plus 2 whole upon 3. So in the first step, we will prove that it is true for n equals to 1. So here we write for n equals to 1. LHS is n into n plus 1 and put the value of n equals to 1. So 1 into 1 plus 1, that is 2. So for n equals to 1, LHS is 2 and the value of RHS, in RHS we will put the value of n equals to 1. So n plus 1, n plus 2 upon 3. 1 into 1 plus 1 into 1 plus 2 upon 3. So 1 into 2 into 3 upon 3, 3 and 3 cancelled and we get 2. So for n equals to 1, LHS equals to RHS. So it is true for n equals to 1. Now in the next step, we suppose let it is true for n equals to k. So put the value of n equals to k on both the sides. 1 into 2 plus 2 into 3 plus 3 into 4 plus dash dash k into k plus 1 equals to k into k plus 1 into k plus 2 upon 3 and name it first number equation. Now to prove it is true for n equals to k plus 1. To prove it is true for n equals to k plus 1, we will write the term up to k. So 1 into 2 plus 2 into 3 plus 3 into 4 plus dash dash up to k into k plus 1. And to write the next term, k plus 1th term, we will write k plus 1 at the place of k. So this becomes k plus 2. And on the right side, k plus 1, this becomes k plus 1 plus 1 means k plus 2, k plus 1 plus 2 means k plus 3 upon 3. And we prove LHS equals to RHS. So by taking LHS up to this term from first number equation, we replace this whole term by k into k plus 1, k into k plus 1 into k plus 2 upon 3. And the last term would be written as it is. That is k plus 1 and k plus 2. Now from these two terms, we take common. So from these two terms, k plus 1 and k plus 2, both are common. K plus 1 and k plus 2, both are common. So it remains from first term, k by 3 and plus 1. So k plus 1 into k plus 2, and by taking LCM 3, we get k plus 3. So the result comes to be k plus 1, k plus 2, k plus 3 upon 3, and that is RHS, which we have to prove. RHS k plus 1, k plus 2, k plus 3 upon 3. So in the very last, we will write that it is true for n equals to k plus 1, because we are getting LHS equals to RHS. It is true for n equals to k plus 1, hence it must be true for n equals to k and n belongs to capital N. Now the next question, question number 7. Question number 7. 1 into 3 plus 3 into 1 into 3 plus 3 into 5, 3 into 5 plus 5 into 7 plus dash dash 2n minus 1 into 2n plus 1, 2n minus 1 into 2n plus 1 equals to n into 4n square, n into 4n square plus 6n minus 1 whole upon 3, whole upon 3. So in the first step, we will prove that It is true for n equals to 1. So for n equals to 1, LHS means the last term of the LHS, that is 2n minus 1 into 2n plus 1, and we put the value of n equals to 1. So 2 into 1, 2 minus 1, 1, and 2 plus 1, 3, 1 into 3, 3. So we are getting LHS equals to 3 for n equals to 1, and RHS, put the value of n equals to 1 in n 4n square plus 6n minus 1 upon 3. So 1 into 1 square, 1 into 4 plus 6 minus 1 upon 3, that is 10 minus 1, 9 upon 3, 3. So both LHS and RHS is 3 for n equals to 1. So it is true for n equals to 1. Now we suppose that let it is true for n equals to k. So 1 into 3 plus 3 into 5 plus 5 into 7 plus dash dash 2k minus 1 into 2k plus 1. At the place of n, we have substituted k equals to k into 4k square plus 6k minus 1 upon 2, and name it first number equation. To prove it is true for n equals to k plus 1. So we write the term up to k term first. 1 into 3 plus 3 into 5 plus 5 into 7 plus dash dash 2k minus 1 into 2k plus 1. Then to write the k plus 1th term, at the place of k, we will put k plus 1. So it becomes 2k plus 2 minus 1, means 2k plus 1. And this becomes 2k plus 2 plus 1, that is 2k plus 3. And on the right side also, we put k plus 1, 4 into k plus 1 the whole square plus 6 into k plus 1 minus 1 and whole upon 3. So 1 into 3 plus 3 into 5, 5 into 7 plus 2k minus 1 and 2k plus 1 plus 2k plus 1 into 2k plus 3 equals to k plus 1, and 4 into, remove the bracket, so k square plus 2k plus 1 and plus 6k plus 6 minus 1 and whole upon 3. Then we solve again. K plus 1, 4k square, 4k square, then 4 into 2k, 8k plus 6k, 14k, 4 plus 6, 10, 10 minus 1, 9 upon 3. So RHS, this we have to prove. So we will solve LHS. And up to this term, from equation number first. हेलो
जी भाई साहब।
हाँ भाई साहब, मैं 10 मिनट में करूँ थोड़ा सा क्लास में।
हाँ ठीक
ठीक। So up to this term, We will write from first k into 4k square plus 6k minus 1 upon 3 up to this term, and this term would be written as it is. So plus 2k plus 1 and 2k plus 3, 2k plus 1 and 2k plus 3 as it is. Then we take LCM. We take LCM. So LCM will be 3 and this term is multiplied by k. So 4k cube. 4k cube plus k into 6k. 6k square minus k plus 3 multiplied by 2k into 2k, 4k square plus 6k plus 2k and plus 3. So 4k cube plus 6k square minus k plus 3 into 4, 12k square plus 8k into 3, 24k plus 9 upon 3, and it becomes 4k cube plus 6k square plus 12k square, that is 18k square, 24k minus k, 23k and plus 9 upon 3. When we remove the bracket of the RHS, then we get k into 4k square, 4k cube plus 14k square, 14k square plus 9k plus 4k square plus 14k and plus 9 upon 3. Then 4k cube as it is, 14k square plus 4k square, 18k square and 9k plus 14k, 23k and plus 9 whole upon 3. So this is RHS and this is also RHS after solving LHS. So LHS equals to RHS, hence it is true for. Thus it is true for n equals to k plus 1, hence it must be true for n equals to k and also true for n belongs to capital N for all natural numbers.